All right, let's go ahead and get started. Thank you again for attending Build and for attending our session, Understanding Connected Standby. My name is Pat Steeman. I'm a lead program manager on the Windows core team. And today what I'm going to do is I'm going to walk you through how we think about Connected Standby, kind of bottoms up, if you will, from a hardware point of view. Now the good news is Connected Standby has already got a lot of attention here at Build. You saw Mike demo it in his portion of the hardware keynote yesterday morning. He did a demo on a Qualcomm platform and showing the power meter. We also heard about it in Dennis's session this morning in the big picture session about building great Windows 8 systems. In fact, even my session is about 45 minutes of the tight integration between hardware and software to deliver low idle power and enable the connected standby experience. But I'm here to tell you that it's really all about the applications. As much as hard work goes into the hardware, to the integration, to delivering low idle power, the whole reason we are doing connected standby is all about the application experience. You want an application that is fresh, that's up to date, that has your current content. And just to belabor the point, I want to go back to a screen you guys have seen so much in the last 24 hours. Look at this thing. It's alive. It has recent content on it. It has the current weather, in fact, in my hometown in Ohio. It has stock prices that are current. It has context about, in this case, we have the Build application, about the most popular sessions. That data is alive. It's fresh. When I come back to the machine and I turn it on, and I have that instant-on experience, I don't want to wait to associate to the network. I don't want to wait for it to synchronize. I don't want it to wait to download, and I don't want it to show stale data. Connected Standby is about showing the fresh data every time, the fresh information in that application, immediately when you turn on the PC. It's really, really, really about the applications. Now the plan today is we're going to walk you through the difference between Connected Standby and Standby and Hibernate as we know about it today on Windows 7 PCs. And the way we're going to do that to start with is we're going to look at actual power measurements from a Windows 7 laptop and from my Windows Phone 7 as kind of an analog for the Connected Standby experience. I think kind of an interesting way to see the differences between a platform that does standby today and something that does something like a Connected Standby. And then we're going to talk to you about the significant investments we've made in Windows 8 to enable the Connected Standby experience. I think there are 4 key things from a hardware and a software point of view to enable a Connected Standby, and we're going to talk about them in detail. We'll be as clear as we can about the app model, both for Metro style and for desktop applications and how they're impacted by Connected Standby. Stephen Berard from the Windows Core team is going to come up and do you a demo of Connected Standby on a different platform that you haven't seen yet to kind of demonstrate the point that it's not just about one piece of hardware or one system. And then finally, we'll talk about what the requirements are and what makes a great Connected Standby machine. You're going to find, and I'm going to say again and again, that Connected Standby is consistent. It's consistently long battery life. And we have a set of tests to help enable testing for that and validation and a set of requirements to make sure that platform is as good as it can be from a battery life point of view. And of course, we'll take your questions as time allots at the end. I think the key enabling point of a hardware platform and a mobile PC that enables Connected Standby is ultra-low idle power. Ultra-low idle power that can be entered in and out of much more like a processor idle state than a system sleep state. The capability to go from active power to do work, to synchronize content, to handle incoming notifications, back down again to an ultra-low idle power as quickly as possible. And if you think about the attributes of one of these hardware platforms, you can see that they have low power DRAM. They have low power buses and devices. There are a ton of topics, I'm going to show you some at the end, sessions here at Build to talk about low power devices, things like Bluetooth LE, work we've done in the USB stack, sensors, other things that are really about low power. That device is always connected to the internet. The way that you get a fresh experience when you turn it on is that the content was already delivered. And the way that you get that is that you're always connected. That enables both the constant synchronization and support for real-time incoming or push notifications. Again, it's all about the application experience. I turn that device on and instantly it comes back and all of my application content is there. It's the content that's location aware, it's for me, where I'm at now, the current market price, those kinds of things, fresh, up to date. And as you've seen and we've belabored, PCs that are capable of Connected Standby, they transition in and out of the Connected Standby state instantly, rapidly, very fast, very fluid. as fast as your phone, and in many cases faster than what we see from Standby and Hibernate on today's PCs. And again, the key enabling point, very, very low idle power. It's not just a hardware thing to get to low idle power, as we'll see. There's a bunch of software enabling work and a bunch of operating system work to do as well. So this is pretty cool. This is a lot of fun. I wanted to kind of show you the difference between a Windows 7 PC and its power output from a sleep state, and also from a pretty good analog to connected standby a phone. In fact, I took my, this is a Samsung Focus. I took my phone apart on my kitchen table a couple weeks ago, measured power on it, kind of almost broke it in the process, but it still works, so it's all good. And the PC that I'm showing you here is a Samsung Series 9 that's on display downstairs, and it's a great Windows 7 machine. It's a fine Windows 7 machine. And what I've done on the charts is I've configured them both to turn off the display after 3 minutes. Those of you that are familiar with Windows 7 power management, you know that we have different levels of display and sleep idle timeouts in the system. So if you look at the top chart here, what we've got is that a machine that's configured to dim the display after 60 seconds, and you can see a reduction in power after the display is dimmed. And that PC is also configured to turn off the display after 2 minutes of inactivity. So 60 seconds later, it spikes up to do a little bit of work and then drops down to a low power again. First key point is display has huge impact on system power consumption. I think we all know that, but really can't underestimate the amount of impact a display has on battery life and power consumption. And you can see after 3 minutes, that machine goes into a sleep state. And when you talk about that sleep state, we call it S3. It's an ACPI-defined sleep state called standby or sleep. And the key thing about it is while it has, relative to on, has a low idle power, no code executes while the machine's in S3. All your context saved in memory, memories in self-refresh, and you've got a number of wake devices maybe armed. So you can open the lid, hit the button, maybe have incoming for wake on LAN in some cases. But that thing is flat. Nothing is happening while that machine's in S3. But look at the phone. So the phone starts, I configured it to turn off my display and lock the phone after 3 minutes. The first thing that happens is you can see this little dip after about 30 seconds. That's the phone reducing backlight power. In the Windows Phone 7 model, they leave the machine with the screen on for 3 minutes, and then 180 seconds, it goes down. And in their screen off mode, which in my opinion is not a good analog for connected standby, look at the difference in the power curve. In the S3 case, the machine is flat, consistently same power. But in the phone case, there's little blips. There's little pieces of activity. While it has a very, very low platform idle power, it still does work. There's still things happening. That's your cellular radio connected. That's your Wi-Fi device maybe connected. I had it connected to my home network. Maybe you're getting an email. Maybe you're ready for an SMS message. There's still activity, but we all know that our phones, they last for a fairly long time in that standby state, in that screen off state. This is probably the easiest way to illustrate the difference between standby today and a connected standby. Rare code execution when the screen is off. Well-managed code execution. Constant connectivity to the network, and still very, very low platform idle power. Now, before I get too much farther into what connected standby is and how it works and the 4 things that I think are most important in enabling it, kind of wanted to do some basic mechanics, kind of get us all on the same page about how connected standby works. I think that a machine capable of connected standby has 3 power states that it's used in primarily. The first one, the green circle here on the left, screen on. I think that's pretty obvious. The screen's on. Most of your PCs have that today. Then there's a shutdown state. 0 watt, context lost, no state saving, but the machine is completely shut down. The middle state, the one we're going to talk about the most, that thing's connected standby. And my opinion is that for a machine capable of connected standby, that will be its predominant default off state. When the user's done with their machine, they're going to press the button. It's going to go to connected standby. When they want to use it again, they're going to tap the button, come right back on. All your content's there, apps are live, tiles up to date. I think it will be very, very rare that a user shuts down a connected standby capable machine. The predominant scenario will be probably a reboot, either for servicing or update or additional device installation. Now, when you think about how you get in and out between the green circle and the orange one, how you get in and out of the connected standby state, it's very much what you would expect. You can get there by pressing the power button, instantly go to connected standby. If you sit the device down, walk away from it, we'll idle into connected standby after some amount of time. It's probably going to be pretty aggressive in terms of how fast we're going to want to idle it out because the display has such a big impact on mobile system power budget. You want to get out of connected standby? The obvious things work. You press the button. Maybe you have an input device. Maybe this thing's in a dock. Maybe it's got a keyboard, Bluetooth, something like that. Tap, tap, wakes up out of connected standby. Seems reasonable. You might imagine that there might be times we exit out of connected standby to deliver an incoming notification. Maybe you're about to get a VoIP call or some other kind of real-time incoming event. The last bullet, though, is probably the most important for us to remember as we talk through the rest of the conversation. We've modeled connected standby as the system is logically on. It just so happens the screen is off. And that's so important because from a user's perspective, when the screen is off, the whole machine's off. The whole machine is off and it has battery life consistent with an off experience. It lasts a very, very long time in that off state. And it's consistently long time. It's not some days it gives you 8 hours of off and other days it gives you 8 days. It has to be consistently long, low power when the screen is off and in connected standby. So very important. And when we talk about all the investments we've made, all the frank dependencies we have on the hardware platform, we talk about the application model, all designed to deliver consistent battery life while the machine looks off to the end user. Dennis used this slide a couple of hours ago, and what I've done here is I've measured that same Samsung PC, again, a great Windows 7 machine, and I've measured its power consumption, idle, screen off. I just said connected standby is modeled as the system is on, but the screen is off. So I thought, let's measure a Windows 7 PC and see what it looks like. This is real-time power data from our power lab. And you can see it's pretty dynamic. It changes power a lot relative to what I think a conceptual connected standby power curve should look like. It's changing a lot. Some of that's frequent timers that we have in Windows 7. Some of it's the periodic tick. Last session, a gentleman asked Sharif and Jason about the 15.6 millisecond timer tick. You know, that's some of the activity that's happening as the platform is transitioning in and out of processor idle states. Very, very active dynamic power curve. But when you think about what it takes to deliver long, consistent battery life in connected standby, that power curve has to look completely different. First of all, it has to be very low. And those pieces of activity to wake periodically, to either handle some application synchronization, to handle some incoming event, they have to be really, really short-lived. They have to be very, very fast. There's some constant, I've shown these with little lines in the diagram here, but there's going to be some constant draw to keep the Wi-Fi or the cellular communications device on. These devices are always connected. And what we'll learn as we go farther into the conversation is that the connectivity is offloaded. It's transitioned down into the connectivity device, whether it be the cellular radio or Wi-Fi, to keep the system constantly connected to the internet. And there is some frequent activity that happens there, but it's so small in terms of power consumption, so very, very small to keep that maintenance. Now, when you look at the differences in the power curves, I think there are 4 things to get you from the green one to the orange one. And that's what I want to talk with you about for a little bit. The first one is I think you have to have great device power management. When you look at the kinds of platforms, whether they be SoC-based or not, that deliver a really, really low idle power for connected standby, you have to have great management of the devices, both inside the core chipset and outside in the design of the system. You have to have those devices turning off when they're not in use. You have to have support for fine-grained idle, for clock eating them, for turning them up and down as fast as you possibly can. And you'll see that we have to have support to encompass the diversity in the silicon solutions that are very low power. There's a lot of diversity in those, and it's really important that from an application and device point of view, we insulate from the power differences. The second thing you've got to have is you've got to make those spikes, those orange pieces of activity that we're doing periodically, you've got to make sure that those are the least amount of application activity that you can do and still deliver a compelling user experience. We call that work idle hygiene, or getting idle and staying idle. A ton of work to get rid of the periodic activities. That 15.6 millisecond timer is probably the first one we took care of for Windows 8. If you think about this activity that I'm talking about, you've seen it in the demo, you've seen these little spikes, these coalesce timers. It's all about this work that we're going to do to keep the machine fresh and up to date. The width of that work is really, really important. You need to do as little work as possible, just like I said, to get great battery life. Another way that you can work with that is you have an application model. I like to say the Metro-style application model. It's right by design for power management. It's right by design from the get-go, from the template, from the start, to deliver great battery life. Super, super important. And the last thing you need is a set of connectivity enhancements. You need the capability for the Wi-Fi device, for the cellular radio, for other connectivity modules to keep that device continually connected to the internet while the core chipset or the SoC is predominantly off. Super, super important. Those connectivity enhancements go starting at the Wi-Fi device or the cellular radio and go all the way through our networking stack. In fact, there are 2 sessions here at Build talking about them. One of them is Wi-Fi specific with Drew Barron, and another one is about the core networking stack, and Andrew Ritz is going to be presenting that tomorrow afternoon. Super, super important to enabling the connected standby use model. So again, it's about these 4 key investments, about taking a machine that's modeled as screen on, or screen off rather, but logically on, taking it and having it look with a power curve that delivers long battery life. Constant connectivity, very rare, very well-structured code execution. First thing I think you need is a great device power management story. And we have the pleasure, I would say, of working with a number of silicon partners and a number of device partners in building really great connected standby capable systems. But they each have their own special sauce, if you will. They each have their own value add, their diversity. The difference is in the underlying hardware that enable great device power or great system power management for their solutions. The first thing and job number 1 from a device power management point of view is I want the applications that are built, whether they be Metro style or otherwise, I don't want them to know anything, frankly, about the underlying device power management architecture, the underlying special sauce, the underlying complexity in managing the core chipset or the SoC. I think it's super important that we insulate those applications from those changes so you can build them once and they run across the breadth of our platforms. The pattern that we use to encapsulate that diversity is really a port mini-port pattern. It's the capability for Windows to have a port driver that encompasses most of the functionality or the generic functionality. Make sure that those driver interfaces, whether they be for other parts of Windows or for applications, are consistent. You see that with USB is a great example where our interfaces for applications to talk to a USB device, they're consistent across all the platforms that implement a USB host controller. What we've done is we use these port mini ports for as many devices on the platform as we can, but from a power management point of view, we've made a new mini port. We call it the Power Engine plugin, or some of you have heard me call it the PEP. It's essentially a power manager mini port. It's a device driver that's loaded in kernel context that makes it easy for the power manager and for devices on the system to talk with that PEP, to give it information about when devices are in use, and to have that PEP handle the complexity, the special sauce, the power domaining for any given piece of silicon abstracted from everything else in the operating system. The other good news for for the PEP is that the PEP is built with new interfaces. We call it the Windows Power Framework. But those interfaces allow drivers to talk to the PEP very quickly, very frequently. They can have very, very fine-grained power management. A function block can be clock gated maybe 10 times, maybe 100 times a second. So you're always delivering the lowest power possible, whether we're talking about connected standby, talking about screen on idle, talking about web browse. It doesn't matter what the workload is. We want the platform to have the lowest power consumption at any given point in time. And this fine-grained, this rapid, fast power management is just super key to delivering that. I think the key point about device power management is that we want to make sure the differentiation is enabled. We want to make sure that our partners can differentiate in their silicon, in their devices, in their firmware to deliver great power management. But we want to keep it away a little bit from the application. We want to keep it away a little bit from the application and driver runtime or interfaces. And you can see us kind of pushing that in my picture here. You can see us pushing that to the sides with port mini port, pushing it down into the firmware to help describe the devices. Really, really important when we talk about enabling a connected standby capable platform, enabling a platform with ultra-low idle power, is to enable that diversity, enable that low power, but do it in a way that prevents the applications from really having to feel or see or be aware of it. So that's step 1, great device power management. Step 2 is you got to maintain constant connectivity. In fact, that's so important. We have a bunch of sessions here about it at Build. Now, one of the things that these ultra-low idle power platforms do is they feature offload technology. It's the kind of the idea that you use the lowest power part to do the work you're doing. And typically offloads get talked about in a multimedia context. People talk about audio offload, about video decode offload, sometimes about video encode offload. It's all about doing the right work at the right place from a power point of view. And to keep constant connectivity on the internet, what we do is we offload the connectivity maintenance. We offload it to the Wi-Fi or to the cellular communications device. And here in my animation, I've got that Wi-Fi device doing some amount of work while we're in connected standby. And every once in a while, we'll figure out we have an application that needs some synchronization. We'll have a push notification that'll come in. We'll have some amount of work to do, and we'll end up having to light up the entire system to do that work. But we still want to do it very, very briefly. With any luck, my animation will help me out here. In a few seconds, we'll light up everything, whether it be the storage to hit to save some content, whether it be memory to access something, or the chipset itself. Really, it's about keeping the Wi-Fi device on in a very, very low power state and trying to keep everything else off or in an idle state as long as possible. Let's see if we have one more animation just to make the point. Okay, well, not cooperating, clearly. There's a lot of technology that goes into the Wi-Fi offload, into the cellular offload work. Definitely encourage you to check out the other sessions we have on that here at Build. I'm going to show you at the end of the content here the session numbers to attend, but just really, really critical to keeping that constant connectivity on the system and keeping low power at the same time. Now, the cool thing about the offload technologies that we've built, they're not just about connected standby. They're not just about screen off idle. We also apply a lot of them while the screen is on to get even better power efficiency when the customer is using the machine. So that was the second thing. So device power, constant connectivity. The next one I want to talk with you about is idle hygiene, or we've also called it getting idle and staying idle in past conversations. When you look at the power budget or the power model or these little spikes and the flat lines for connected standby, the key driving factor in how long your battery life is going to be is how low is that floor in terms of power consumption. The next driving factor is going to be when you do wake up to do some work. How often do you wake up? How long has it been since the next one? And how much work do you do? So we're going to zoom in and take a look at one of those spikes and talk about the things that influence the power consumption of one of them. So you can see I've got just one isolated here. I'm kind of in a graph, and you see the dotted line. There'll be another one in the future. The first thing that we want to do from a software and hardware point of view is we want to make sure that you don't have to exit that deep idle state unless there's something really, really important to do. So the first thing that we did is in Windows 7, we had this 15.6 millisecond timer. Ran all the time. First thing we did is remove that. So now we have a solution that wakes the processor up out of its idle state only when there's some work to do. There's other ways to eliminate exit events as well. You want to have this Wi-Fi offload technology is essentially an exit event eliminator. It's about having that Wi-Fi device process connectivity, only wake when there's something important for an application to do. Another good example is that a lot of the platforms we're working with, their device interrupt patterns are really, really good. They only interrupt the main CPU or interrupt the main chipset when they have something important to do. The second thing that you can do is you can reduce the software activity. So once you're awake from a connected standby point of view, you want to do as little as possible. And I assert that the most important thing here is the Metro-style application model. We've built that application model, again, right by design for power management, so that only the set of well-behaved, coordinated, policy-controlled, if you will, application behavior runs when the machine's awake. We really, really want to have a consistently long battery life experience, and doing that requires that only well-structured application activity runs when the machine's awake during connected standby. The other thing that we've done is you've heard folks talk about coalescing. I think that's really about extending the idle duration. The platform budget is all about how long can you stay in that idle state. Plus, a lot of the silicon and the power models, they have a penalty, frankly, from waking up from the idle state to the active state. And you want to make sure you amortize that across a long amount of idle. We don't want to be waking up every 15.6 or even waking up every second. We have to be very, very quiet to get great connected standby battery life. And so the third thing that we've done is we've really tried to extend the idle duration. A lot of that's idle hygiene, work that Sharif and Jason did and talked with you about last hour in terms of working through the operating system, finding things to clean up. A lot of it's the background tasks that are allowed to execute as part of the application model. They're also sort of coalesced by default to make sure that we wake up infrequently to do a background activity. The automatic maintenance feature is about that same thing. They talked with you about that last hour. We've also built a number of what I would call resiliency technologies to enforce a minimum idle duration on the platform to make sure, again, we get that consistently long connected standby battery life. The net of all of these, the net of can you eliminate the exit events, the net of can you reduce the software activity, the net of can you extend the idle duration, that's going to tell you how long your battery life is. There'll be an average power. When you average across these peaks of work and the power floor on the machine, you'll end up with an average power for connected standby. And that's going to, frankly, when you combine that with the size of the battery, that's going to tell you how long your battery life is going to be while you're in this mode. Probably the best conversation about this slide happened a couple of hours ago in Ben Schrower's talk on the MetroStyle application model. Again, the MetroStyle application model, we've done a lot of work to make sure that it's easy for developers to build power-friendly applications. He talked a lot about while the screen is on and as applications come into the foreground and go into the background, how they're suspended and resumed. And the point that I wanted to make for connected standby is that all the applications in the MetroStyle applications, they're all suspended while the machine's in connected standby. We do have provisions for those applications to get notifications, to update their tiles, to do some amount of scheduled background activity on a periodic basis. We have those things. We call them background tasks. We've tried to make them as easy to implement as possible. We've tried to coalesce them, so again, we extend those idle durations. We've tried to make it very easy from a networking point of view to make sure that those notifications work seamlessly. They're batched up, they're delivered in a power-efficient way. And there are ways for applications to do background activity. A lot of the questions in the last session, I think, were about a concern that in connected standby, nothing could happen. I think we realized that a compelling mobile experience is about those fresh applications. And that requires some amount of background activity. We just want to make sure we do that in a controlled way, in a way that gives the consistent battery life, gives the user a consistent connected standby experience. There's a lot more information. There's another talk tomorrow around how to use the background task API for notifications for updating your tiles. I encourage you to attend that, and we'll have that in the list at the end of this session as well. But from a power point of view, I can't tell you how excited I am about the application model. Just super, super important for us that we make it really easy to do applications from a power point of view, to do great applications, immersive applications, and still have great battery life. And I think that transitions us to an interesting comment about desktop applications, about Win32 applications. Now, I've worked on power management for the 8 years that I've been here at Microsoft, and a lot of the conversations I've had at previous conferences with our silicon and application partners have been about getting power management right for the Win32 application model, getting battery life right for existing desktop applications. I'm going to be honest with you, it's pretty hard. It's really, really hard to do well. It's not easy. It's not simple. It's not automatic. It is doable. We've done it in our own applications. We work with a number of partners. They can do this, but it's much more challenging than what we've made the MetroStyle application model out to be. It's much, much easier in the new application model. If you think about connected standby as logically on, but the screen is off, I'm going to have a pretty big problem with the breadth of software that's out there today that can be installed from a desktop app or a Win32 point of view. So we've built what we would call a resiliency feature called the Desktop Activity Moderator, or Desktop Activity Moderation. That's all about when the machine is in connected standby, making sure those applications, those desktop apps, they're suspended. They're suspended just like a modern MetroStyle application is suspended. They're suspended so they don't have impact on battery life. They're suspended so they're not running, consuming CPU cycles. As an application developer, if you're building a desktop application or service, nothing you have to do. It just magically works. Guys on the performance team took care of this for you. Your application is just going to be automatically suspended. A lot of questions came up in the last session about this, and I'm probably going to get a lot more at the end. We'll talk with you. We're happy to answer those questions. But the good news about this is it's just magically going to be taken care of. If you do have an application, you do have a scenario, you have something that you want to be alive and fresh on connected standby, we need to do that in the MetroStyle application model. All the provisions in terms of easy API, in terms of suspend and resume, in terms of control background activity are there for you. And I guarantee you they're easier to do there than they otherwise would be for a desktop app. So 3 things so far, or 4 things so far. So we talked about idle hygiene, talked about the app model, talked about device power management, and talked about constant connectivity. So what I'd like to do is kind of show you what you're going to get for that. So we're going to show you another demo. Stephen Berard on our team is going to come up and talk through it with you.
Thanks, Pat. Okay, let me get set up real. Whoa. Okay, don't walk in front of the speaker. Let's get my setup here. As Steven Sinofsky said in the keynote on day one, Windows 8 is going to support the widest breadth of hardware out there. We saw a wide variety of systems that Mike and showed on stage in the keynote, from the big servers all the way down to these highly portable devices, highly mobile devices. What I have here is one of our silicon partners, NVIDIA's Tegra development platform. And I'm going to go through and show you some of the stuff that Pat was talking about in terms of connected standby, what we get there, and what it looks like. So the first thing I want to do is I want to say thank you to NVIDIA. We've worked really hard over the past few months, and actually quite a lot longer than that, and a lot of late nights, to get this system running and performing with connected standby. I have the pleasure today to actually show this live on stage. And so I want to talk a little bit about the setup that we have. This is a screenshot of basically the system we have, and it's an NVIDIA Tegra development platform on the side, and that's what we have here. And connected in the back, and you really can't see it, is the special board, and the special board provides the ability for me to measure power in real time. And then we have an application here on the auxiliary PC that's actually displaying that. So I'm going to switch to that now. If I press the right button. Would be a laptop. Is it laptop 2, Pat? Hey, there we go. Okay. So what we have here is we have a screen that's moving. Try that again. What's a demo without demo gremlins? Okay. Sorry about that. What we have on the screen on your left is the power meter. And what we're showing here is system power. And as Pat was showing in those conceptual diagrams, we have this really low idle floor where the system is really quiet for long periods of time, and then we have these little spikes of activity. And this device has actually been in connected standby the entire presentation. And as you can see, there's these little spikes of activity where the system's waking up, doing a little bit of work, and then going back down. This is how we're actually going to get these long battery life, but also keep those apps that are so important to be fresh and up to date. That's how we're going to keep them up to date. That's how we're going to keep them with information that's relevant to what you care about. That's how users are going to be able to turn on their device real quick and see that they have an appointment in 2 minutes. They're not going to have to wait for their device to connect to a network, to sync their mail or sync their calendar, and then have it useful. They'll be able to instantly turn it on, and it'll have the information that they need right away. And so now I'll demo the part of instant on. So when we hit the button here, you'll see very quickly the system wakes up from this low power state, and the screen comes on. And you can see this is the start screen that we would have on our desktop here. And I can swipe, and it's hard to do from this side. I can swipe, and I can see that I'm back at that start screen. Now when I'm done, and I don't want to look at the apps anymore, and I need to go and put it in my bag and run to catch my plane, I can hit the button really quick. And you can see that I'm actually going to go right into this low power state very, very quickly. Now you'll notice just on the edge of that, before I go into that really low power state, is these little tiny spikes of activity. This is where those apps that in Ben's talk, he was talking about the suspend and how apps can save state and checkpoint so that when you go back into that app, I'm exactly where I was before. That's the opportunity for those apps to do the work they need, save that state so their apps appear to be running all the time, and then instantly put the system into a very low power state. And as you can see, we're back in that same pattern again, where we're down in a really low power state for a long period of time, and then spike up to do these little bits of activity. And with that, I'm going to switch back to the PowerPoint and let Pat continue. There you go, sir.
Thank you. So again, we wanted to thank NVIDIA for letting us have a system to demo and for a pretty compelling power demonstration for you. I want to take a few minutes and talk about designing a great connected standby mobile PC. It kind of bleeds off the screen up here, but it says mobile PC. I think that it's super, super important when we talk about a device that does connected standby, that we talk about a device that's consistently long, I've said that like 6 times now, consistently long battery life while it's in connected standby. And we have I would call it a minimum bar in mind, a belief that long battery life, it's off. The machine looks off to the end user. It feels off. It's got to have a battery life consistent with the off experience. And we've got a number of tests in our certification program to help you validate that the system gets great connected standby battery life. The first one is we have a test that will validate that the system drains no more than 5% of the system's battery over 16 hours. And let me talk about how we got to 5% over 16 hours. If you think about a standard business day, a day that ends at 5 p.m., a day that starts at 9 a.m. the next day, it's a 16-hour period. And our belief is that the user will not tolerate any more than a 5% battery drain over that period to get the connected standby functionality. And these platforms that have low-power DRAM, have low-power buses, devices, they have non-rotational media, they have like flash or solid-state drive. Those things, I think, are going to very easily attain the 5% number, very easily going to meet this requirement. It's really, really important when you think about these peaks and the background activity model and the promise of an instant on and instant off experience. We believe it's really important that the responsiveness of the machine is less than 300 milliseconds from when you touch the button to when the screen lights up. Not only does that help us have the instant on experience for the customer when they turn the device on, it also helps us make sure that those little peaks of activity, they're optimized from a power point of view. We don't want to spend seconds or minutes trying to get the machine up and running so we can do a little bit of background activity and then put it back down again. That exit from the low power idle state up to doing activity has to be really, really fast to make sure you have time to do that freshness of applications to keep them up to date. Now, connected standby doesn't work on platforms unless there are a couple of basic things that are met. The first is that the platform has to tell us it's connected standby capable. We defined a new ACPI, a new firmware flag that allows the platform to tell us that it's capable of connected standby, that it would prefer to remain in the on state over perhaps using something like standby or hibernate from an idle or a power point of view. The other two things is that you need a non-rotational boot volume. This is a mobile machine, can be picked up, put in your bag, put wherever you want. And in connected standby, we might touch the boot volume to save an application's content, to handle a notification at any point in time while it's in connected standby. Super, super important that we don't spin up a rotational drive to do that. It's just a fundamental requirement to making this great from a mobile PC point of view. And the last thing is that in order to make sure that you have that constant connectivity, you have that Wi-Fi offload, devices that have, mobile devices that have Wi-Fi in them, which I'm assuming is going to be very ubiquitous, they need to support a set of features that we've defined in our driver model, which Andrew and others are going to talk with you about tomorrow, to make sure that you can have that offloaded constant connectivity experience. There's one called Wake on Push, which is the ability for the Wi-Fi device to recognize a set of patterns and wake up the core chipset of the SoC when only a matching one is found. And also this capability to do D0 offload, where we can continue to offload some amount of networking activity while the machine is on and running. Just really, really important to enable the connected standby experience. Again, I want to just kind of underscore that connected standby, it's on. The machine's logically on, but it looks off to the end user. Screen's off, it's going to feel off, it's going to behave like off. We don't want indicators around the machine while it's in connected standby. It's got to feel like off when the customer picks up that machine. Just really, really important. We've got a set of tests to help you with this, a set of ways to measure. We're talking with all of our silicon partners about these requirements. They're all up to date with us. They're all on the same page with us about these set of things, these tests, the validation tools. So no surprises all around, but just really, really important. So if there are three things I could have you walk away with, the first is it's all about the applications. Clearly, that's what you're hearing at the Build conference, but even with connected standby, even with the focus on low power hardware, even with the focus on long idle and instant on-off, it's still all about the applications. It's about having that start page be alive, be fresh, have the latest tiles, the latest information. We've got provisions for those things to happen. Metro-style applications, they can use background tasks, they can use push notifications, they can use the scheduled tasks set of APIs to stay fresh and up to date. And then for desktop applications, we solved that problem for you. We're going to just suspend those, just like we would for sleep or hibernate, and there's nothing that you're going to have to do to handle those. These are the most important things you could walk away with for connected standby. There are a number of related sessions here at Build, some that are after today, and a lot of them are tomorrow. Sharif and Jason, they talked with you last hour about generically working on battery life and energy efficiency and having great performance. I encourage you to review that one. It'll be streaming and online. There's a number of sessions about low power buses and devices. There's a Bluetooth session. There's a number of Wi-Fi sessions, network connectivity sessions, using the tiles and notifications to stay up to date. And then Dennis's big picture talk this morning about building great Windows 8 systems, pretty important too. So with that, again, thank you so much for coming. Thank you so much for trooping all the way over from the convention center. Thank you again to NVIDIA for loaning us a platform to demonstrate. Just really, really appreciate everybody's attending and a full room. So with that, we'll take your questions as time allots. What we'll probably do is take about 5 minutes of questions if there are that many, and we'll tear down for the next set of presenters, and we'll go on from there. Thank you again.
Hi there.
Hi.
So my question is about heat.
Okay.
I'm wondering if you've gathered any metrics on the relative, how much heat is generated relative to, say, a true S3. Because me personally, when I see this thing in an off-like state, I'm going to want to throw it in my bag.
For sure.
And move with it. So
For
I'm
sure.
just wondering if it's in danger of
I think that
overheating.
from all aspects, so the question was about thermals and about heat, connected standby relative to S3, I think is the question. That's a very awesome question. This device looks off. It might be connected and still might be doing work, but it looks and feels off. And my expectation is that the power consumption, which I think is a good analog for thermal, will be probably significantly better than S3. If you think about the kind of battery life you need and the low power you need to have really, really long connected standby battery life, it's going to have a power consumption that I think in most cases is going to be much better than S3 is today. So any thermal that should come from that power consumption should be less. I think we were designing the system, and if you talk to any of our silicon partners that are working on similar technology, I think they would tell you that, and I would hope they would tell you that, it's got to look and feel off. It's got to be like their phone. I don't want, if a customer takes a connected standby machine and shuts it down before they put it in their bag, I think I've probably done a bad job. It's got to feel like off. Really, really important. There are microphones. Prefer you, if we can use the microphones, that'd be great. There's one question in the back, and then we'll see if there's some more.
Hey, Pat. Just a question on the demo.
Sure.
Was that having a Wi-Fi on at the same time, and was DAM there, or just maybe a little more details there?
So in this demo here, we actually are not connected to the Wi-Fi network here, just where we are, but the network adapter was on in that particular demo. We don't have we're not demoing the network offloads. That'll be done in a session later. I believe it's tomorrow afternoon, and they'll show how that works. But on this particular system, we did not have that running today just because we didn't have the Wi-Fi here in this room.
Okay. And DAM was also...
Yep. But DAM was on. In fact, in this demo, the Wi-Fi adapter was fully on that entire time. It just wasn't associated with the network access point.
Right, 'cause
we
otherwise
think
you'd
that
see
it'll actually be better when you
Yeah.
actually do get the offloads on. You'll actually see an even lower power curve than what we were able to show today.
Yeah. Okay, thank you.
Yep, great question.
Hey, Pat. Kumar Chinnaswamy. Do you envision the connected standby usage model to also scale up to bigger form factors, including AIOs and desktop? If so, 2 questions around it. What are the requirements for those, and
Sure.
how do you support LAN?
Yeah, the microphone got that question. I do think over time, that is a possibility that the connected standby usage model will scale to all-in-one and desktop. It's frankly not something I'm focused on right now, really trying to focus on the mobile, the battery-powered devices, so hard to comment on some of the other questions there. But I think over time, yes.
So 2 questions. One is the PCs that we got through Build.
That's
Do
right.
those support connected standby?
The developer PCs do not support connected standby.
Okay. And then the second question relates to the services, native mode apps services getting suspended.
Mm-hmm.
Are those actually, so they'll end up getting suspended completely in connected standby? And then can you talk a little bit about, you talked about background processing that could occur.
Sure. So let me think about how to answer that most succinctly. Services that are added to the machine, so desktop applications, in my opinion, include Win32 applications and also Win32 services. We have the whole service model. Those will be suspended during connected standby, and we are looking at ways to make sure they get just enough activity to keep the machine from getting into trouble or getting paused or stuck. In fact, there's a gentleman in the back of the room that will connect you with at the end of the session who's the local expert on that specific technology. And so, yes, that gentleman right there. He's the guy to talk about that. What was the second question?
Actually,
Just that one?
the second.
Yeah.
Yeah.
Yep.
Great presentation. I
Thank you.
just wanted to find out some of the certification requirements you showed. Are they the same for ARM and x86, or is there a different bar for x86? Because I know definitely there's more performance there, but there's definitely power issues.
One set of requirements. Okay, well, if that's all the questions. Thank you so much for attending. Thank you so much for attending Build. Oh,
Questions.
Wait.
Sorry.
No, one more. Go ahead.
Just one quick.
One more.
So, can you explain a little bit? So you mentioned about the system risk. What about all the device? So is there any specific power state for the device?
Sure. Sure. So the question was about, hey, you talked a lot about the core chipset and processor idle kind of things, but what about devices? Well, a lot of the platforms that have low enough idle power to enable connected standby, a lot of the peripheral devices and host controllers, they might be integrated on the core chipset already. And the concept of taking the platform and putting it in its lowest idle state encompasses all of those devices. But I will say that if you take a tablet or a clamshell device and try to make it do connected standby, all of the devices in the plastic, not just the core chipset, but all the devices, anything that might be storage, might be DRAM, might be comms, might be off the core chipset, those also have to participate in our power management model. And we're working very closely with all the silicon partners to make sure that their designs, which encompass all those peripherals, are also doing great power management at the same time. So everything has to do it well. Oh, yeah, we can put it back to related sessions.
Where's the?
It's right here. Good.
Forward.
Okay, well, we'll take your questions one-on-one from here. Again, thank you so much for coming.